So today we'll talk about some of the fundamentals that we have studied in our previous lectures. Just we will reconcile what, and then we'll talk about some Einstein photoelectric equation, and then we'll talk about the blackbody radiation. Okay, because in quantum mechanics, the reasons for the failure of classical physics and the existence of quantum mechanics is there are certain phenomena where the classical physics has failed. Right, there are certain cases where the classical physics has failed, and the reason that quantum mechanics has come into existence. Right? So some of the reasons for one is the stability of the atom. There is blackbody radiation, photoelectric effect, Compton effect, Wien's law, displacement law. There are so many factors which the classical theory has not successfully explained. Classical theory has not could not successfully explain them, and then quantum mechanics had some explanation, some favorable explanation for these type of phenomena, right? So one of the phenomena is blackbody radiation, and before studying blackbody radiation, we need to study what is Einstein photoelectric equation, right? So if you study about this Einstein photoelectric equation, right? So we know that in the previous lectures we have seen that Einstein photoelectric equation, that is that is photoelectric effect. The photoelectric effect is a phenomena of liberation of electrons. From the surface of a metal. Right? Some surface of metal, when we insert some light energy on that particular metal. So the photoelectron will have some work function, that is what phi equals to h nu naught that we have seen, and we have seen the verification of photoelectric emission based on the Einstein photoelectric equation, that is half mv square equals to h into mu minus mu naught, and if u is less than mu naught, then half mv square maximum is negative, which is not possible. Therefore, for photoelectric emission to take place, nu should be greater than v naught, right? So u should be greater than nu naught, right? So therefore, since one photon emits one electron, so the number of electrons per second is directly proportional to intensity of incident light. It's clear that half mv square maximum is directly proportional to v, and as h and u naught are constant, this shows that kinetic energy for electrons is directly proportional to the frequency of the incident light. So photoelectric emission is due to the collision between a photon and an electron. Right? As such, there cannot be any significant time lag between the incidence of photon and emission of electrons. That is, the process is instantaneous. It is found that the delay is only 10 power minus 8 seconds. So that is what the Einstein photoelectric emission, which we have studied in our previous lecture, right? And we have seen certain applications of photoelectric effect. So though applications of photoelectric effect are, first one is the automatic fire alarm, so automatic burglar alarm, the scanners in television transmission, reproduction of sound in cinema film, right? In paper industry, to measure the thickness of the paper, to locate flaws or holes in the finished goods. So it is also used in astronomy and astrophysics, to determine the opacity of solids and liquids. Automatic switching of street lights to control the temperature of furnace, photometry, beauty meter to measure the fair complexion of the skin, and light meters used in cinema industry to check the light, and photoelectric sorting and photo counting and metrology. So these are the factors where some of the applications of photoelectric effect. Right. So after studying the photoelectric effect, we need to understand another factor where the quantum physics where the quantum physics has been failed. Right. So those factors where the quantum physics failed is one of the topic is called the blackbody radiation. Right. So in this blackbody radiation, we need to study what is the definition of a blackbody and blackbody radiation laws. The blackbody radiation laws like the Planck's law, right? So which we come under Planck's theory of radiation. Other one is the Wien displacement law, the Stephen Boltzmann law, where we write sigma E equals to sigma T power 4. Right? So E is the energy and sigma is the constant and T is the temperature. Right? So Stephen constant, that is what we call it as Stephen constant. So these are the facts, Stephen constant, right? And other one is the Rayleigh-Jeans law. Right? So these all laws come under the blackbodyation law. Right, and of course we need to go for what are the applications of blackbody and what is the conclusion. We need to study what is the summary of this particular blackbody. So because blackbody radiation is also one of the factors where the quantum physics was successfully explained this particular theory, blackbody radiation. So by taking this particular law, that is a Planck's law, Wheeler's displacement law, Stephen Boltzmann law, Rayleigh-Jean's law, right? So these laws have been successfully explained by quantum theory, where it was unsuccessful by using classical theory. Right. So this photoelectric effect is also one of the factor where people need to understand the emission of electron from the surface of metal. Right. So what is a black body? Black body which absorbs all radiations falling on it. A black body which absorbs all the radiations falling on it is a black body. When a black body is heated, it radiates energy and is called the black body radiation. It's called black body radiation. So a practical realization of black body is also an isothermal cavity painted with a lamp black inside it and contains small aperture such that light enters the cavity through it. Right. So this is what a small hole. This is what the light enters into the cavity. Right. And after taking multiple reflections at the boundaries, it reflects. It comes back to the same aperture as it was entered. So this is what is small hole. This small hole is what we call it as aperture, right? So that's why body which absorbs all the radiation falling on it is a black body. When a black body is heated, it radiates energy and is called the black body radiation. A practical realization of black body is also an isothermal cavity painted with lamp black inside it and contains a small aperture such that light enters the cavity through it. Right. If you see the variation of wavelength with the temperature, we have the wavelength along the x-axis and the temperature along the y-axis. This is the variation for different temperatures. This is the variation that we can observe for different temperatures. That means T1, T2, T3 are the absolute temperature of the black body. Here we have T3 greater than T2 greater than T1. So, and lambda M3 is less than lambda M2 less than lambda M1. So that is the emissive power of a black body in the wavelength range of lambda and lambda plus d lambda. Right? So this is the emissive power between the lambda M1, this is the emissive power at T1, this is T2, and this is recording T3. So these are the factors where we can have lambda M into T is equal to constant. Right? So this is what the black body, general definition, a black body which absorbs all the radiations falling on it is called a black body. When a black body is heated, it radiates energy and is called the black body radiation. Practical realization of black body is also an isothermal cavity painted with a lamp black inside it and contains a small aperture such that light enters the cavity through it. So, right, introduction. The black body is an importance in radiation theory and practice. The ideal black body notion is important in studying the thermal radiation, electromagnetic radiation transfer in all wavelength bands. Right. So the black body is used as a standard with which absorption of real bodies is compared. A black body is an ideal body which allows the whole of the incident radiation to pass through itself without reflecting the energy and absorbs within itself this whole incident radiation without passing on the energy. This property is valid for radiation corresponding to all wavelengths and to all angles of incident. Therefore, the black body is ideal absorber of incident radiation. As we told, if you take one body, right? If you take one body and this black body has certain opening called small aperture. If you allow all the light to enter into that, it takes multiple reflections at the surface and reflects back into the same medium by opening the same aperture to the same aperture in which the light has been entered. Right? So this is what we call it as the introductory fact regarding the black body. So black body radiation laws, as I told you, there is a Rayleigh-Jean's law. So it agrees with experimental measurements for long wavelengths. So Rayleigh-Jean's law, it agrees with experimental arrangement for long wavelengths. It predicts an energy output that diverges towards infinity as wavelengths grow smaller. The failure has become known as the ultraviolet catastrophe. Right. So the intensity of the light is given by I of lambda comma t is equals to 2 pi c k by lambda power 4, right? So this is what the intensity. Intensity. That is what we need. The intensity pattern. Okay, intensity of the light for different electromagnetic radiation spectrum. So this is for Rayleigh-Jean's law. The Rayleigh-Jean's law shows this is the fact for infrared wavelength, and for ultraviolet range, this is the ultraviolet range, and this is the visible range, and this is for the observed spectrum. In the observed spectrum is for ultraviolet, visible, and infrared. Right. So it is depending upon the intensity is depending upon the factor lambda and t. It's called 2 pi CKT by 4, right? So this is ultraviolet catastrophe. In ultraviolet catastrophe, the formula has also had a problem. The problem was the term in the denominator, that is lambda power 4. For larger wavelengths, it fitted the experimental data, but it had major problems at shorter wavelengths. The ultraviolet catastrophe. Unfortunately, the theory disagree violently with the experiment. So this is what the UV catastrophe, and this is the experimental curve. This is the experimental curve which is drawn between the intensity and the wavelength of the electromagnetic spectrum in Planck's theory, right? So if you have the blackbody radiation, we have another law called Planck's law. Planck's law, we have two forms. That is intensity, that is I of lambda t equals to 2 pi hc square by lambda power 5 by 1 by sc by e power lambda kt minus 1. And as a function of frequency, we have I of nu t. This is function of wavelength and this is function of frequency, right? So variation we can observe in terms of frequency. We have at different temperatures. That is, at T is equal to 100 Kelvin, 150 Kelvin, 200 Kelvin, 253 Kelvin. At highest temperature, the intensity starts decreasing, and the lowest temperature around 250 also intensity. That means the intensity goes on decreasing with variation in the frequency, right? Whereas here, based on the wavelength, the peak in the wavelength is observed at T equals to 300 Kelvin and T equal to 250 Kelvin. The intensity, the peak is very less compared to 300, and if you see for 200 Kelvin, is very, very less when compared to 250 Kelvin. So this Planck law gives a distribution. It gives a distribution function that peaks at certain wavelengths. The peak shifts to shorter wavelengths. Or for higher temperatures, and the area under the curve grows rapidly with the increasing temperature, right? So that means here, if you increase the temperature, the Planck's law gives a distribution that peaks a certain wavelength. The peak shifts to shorter wavelength for higher temperatures, and the area under the curve grows rapidly with increasing temperature. So we have the Planck-Blackbody radiation law, that is called Wien's law, Wien's displacement law. It tells us as we heat an object, its color changes from red to orange to white hot, right? So Wien's displacement law. So it tells us as we heat an object up, okay, its color changes from red to orange or white hot. You can use this to calculate the temperature of stars. Blackbody Wien's displacement law is used to calculate the temperature of stars. The surface temperature of the sun is around 5,778 Kelvin, and this temperature corresponds to peak emission of 502 nanometer. So 502 nanometer, right? 502 nanometer, which is about 5,000 angstroms, and and is the constant of proportionality Wien's displacement constant, and is equals to 2.8977768. So that's what the value, and we have the constant of proportionality when discussing about the Wien's displacement law. So this is what the Wien's law we have at different temperatures, 1200 Kelvin, 6000 Kelvin and 1000 Kelvin. As blackbody heats, maximum wavelength emission shortens and energy radiated increases at all wavelengths. So next one is the Stephen Boltzmann law. Stephen Boltzmann law is what we told you. The Stephen Boltzmann law is the energy produced in a black body is directly proportional to fourth power of temperature. That's what we write, E equals to sigma T power 4, where sigma is the Stephen constant, and gives the total energy being emitted at all wavelengths by the black body, which is the area under the Planck curve. So this explains the growth in height of the curve as the temperature increases. And if you notice that this growth is very abrupt. Therefore, the Stephen constant sigma is equals to 5.67 into 10 power minus 8 joule per second meter inverse 2 and Kelvin power 4, known as the Stephen Boltzmann constant, right? So this is what the wavelength observed between for different temperatures at 508 Kelvin and 255 Kelvin, right? So at the foremost conclusion, we can tell that as the temperature increases, the peak wavelength emitted by black body decreases. As temperature increases, the peak wavelength emitted by black body decreases. As the temperature increases, the total energy emitted increases because the total area under the curve increases. So the curve gets infinitely close to the x-axis but never touches it, right? So this is what for the different spectrum, that is what for UV spectrum, visible spectrum, right? And this is for infrared. So in visible spectrum, we have the power radiated at each wavelength, right? So this is a peak in wavelength, this is a peak in wavelength, and intensity of curve for each temperature, that is at 1215 Kelvin, 1500 Kelvin, 1750 Kelvin, and 2000 Kelvin. We see the variation that is between intensity and the power radiated. Right. And finally, we can come to the some conclusion that a black body is a theoretical object that absorbs 100% of the radiation that hits it. Therefore, it reflects no radiation and appears perfectly black. Roughly, we can say that the stars radiate like blackbody radiators. This is important because it means that we can use the theory of blackbody radiators to infer things about stars. At a particular temperature, the blackbody would emit the maximum amount of energy possible for that temperature. Blackbody radiation does not depend on the type of object emitting it. Entire spectrum of blackbody radiation depends on only one parameter, that is temperature. Temperature is the essential factor to understand the variation, to understand to understand the entire spectrum, right? So this is what the summary of this particular content, and with the next topic we'll come up with a different type of law, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.